I am Omer, and in the next 25 minutes we'll be talking about the web cache deception attack. Now, web cache deception is a new web attack vector that allows attackers to easily expose the private content of application users, and in certain cases, to even take complete control over their accounts. I discovered it a few months ago in various large-scale websites, including PayPal. As you can see here, by just sending a simple GET request to the PayPal server without adding a session ID or basically any other cookie, it's easily possible to expose the private content of an application user. So just before we begin, let me introduce myself. So my name is Omer Gil, I am 28 years old, and I am married plus Java. Now, don't worry, you did miss a release of a new web framework. Java is our awesome 2-year-old dog. Now, you probably think now how geek you need to be in order to call your dog after a programming language, and that's not so far from the truth, right? Because if I wasn't a geek, I wouldn't have been standing here talking in front of a hall full of geeks, right, on this geeky topic. But that's not really the case here, because our Java is not named after the language, but after the coffee beans, of course. Now, remember her face, because you're going to see her a lot during this talk. For a living, I'm a penetration testing team leader at Ernst & Young Advanced Security Center. We do penetration tests for web applications, mobile apps, infrastructure, and more. And besides that, I'm a student and just about to have my degree in computer science. So now we can start and talk about web cache deception. And in order to better understand the attack, let's start by explaining two important baselines. And in the first one, we'll talk about caching. Now, we all know about caching. It helps to reduce latency from the web server and to serve the users with their content faster. We all know that browsers do caching, but that's not the kind of caching we're talking about today. What we are talking about today are servers that function as caching mechanisms. Now, let's see a few forms of these kind of caching mechanisms. So for that, here's Java again. She will be our end user. This is a web server on the right, and in the middle, that's a caching mechanism serving this web server. So the first caching mechanism we're going to look at is a CDN, a content delivery network, which is a distributed network of proxies all around the world. While they all cache the application's content, and usually, preferably, the closest group to the user of proxies, which will be the one who will serve him with his content. Now, another form of a caching mechanism is a load balancer. Now, we know that the main purpose of a load balancer is to balance the traffic between more than one server. But what it can also do is to cache the application's content in order to serve the user with it and do it faster. One last form we're going to see is simply a reverse proxy, which functions as the web server front end. It can send requests to the web server on behalf of the user, and in addition, it can also cache the application's content. Okay, so these are all forms of caching mechanisms. Now let's see how the caching process looks like. So let's say that Java here wants to access this page, stylesheet.css. And the request arrives at the caching mechanism. Okay, so now the caching mechanism is not familiar with this file, so it asks the web server for it. Now the web server takes this file and sends it back to the caching mechanism. Now the caching mechanism receives this file, and now it has to decide whether this file should be cached or not. So at first it needs to decide what type of file this is. So it takes a look at the end of the URL, and it sees that it has a CSS extension. Therefore, it decides that this is a style sheet, and if it's configured to cache static files, for example, then this file is now cached on the caching mechanism. Then the file is sent by the caching mechanism back to the user's browser. Now, the next time this user or any other user will try to access this file, the request arrives at the caching mechanism, which is now familiar with this file, so we just send it straight back without asking it from the web server to the user's browser. And this is how caching works. Okay, so this was the first baseline out of two. Let's move on quickly to the second one. Let's talk about server's reactions. So the first time I read about it was when I read about the RPO vulnerability, relative path overwrite, in two blogs, Dispanner and XSS Jigsaw. So let's say there's an application that has this page, account.php. This is an actual page in the application. And the user, for some reason, decides to access this URL. He adds a trailing slash and a name of a non-existent file. So let's see what happens now. So the browser just sends this request. He won't change it. What's more interesting to look at is how the web server interprets this request, the web application. So in certain cases, and not just a few, the web application returns a 200 OK response, meaning the URL stays the same with the content of the user's account page. Okay, so we know that sometimes the web application might return the content of the account page back to the user's browser. But what about the HTTP response headers? Will they meet the dynamic private PHP page or the non-existent CSS file? So same as the content, the HTTP response header, they also match the dynamic private PHP page. As you can see here, for the same URL, the file returns with a no cache directive matching a dynamic private page and not a static CSS file. And you can see that the content type is text HTML and not text CSS, which is expected. Okay, so that was the second baseline, and now we can get down to business. Let's talk about how web cache deception works. So there's, here on the right, you can see a web server hosting, for this example, the web application of Java's bank account. Let me remind you, Java is not the web framework, it's my dog, okay? So it's hosting the web application of her bank account. In the middle, you can see a caching mechanism serving this web server. So there's one thing you need to know about Java, and that's Java has a red-haired evil twin, and she's also a hacker. So one day, this evil twin approaches Java, and she says, "Woof." Now, she's not talking about web application firewalls, okay? Dogs don't do that. This is just how they speak. But let me translate this for you. What the evil twin actually means is, "Hey, Java, can you please access the URL of your bank account?" But in the end of the URL, she adds a name of a non-existent file with a static extension, CSS. So Java is an aware user, okay? She doesn't click any link she receives on Facebook. We taught her well at home. So she takes a good look at this URL, and it doesn't look suspicious at all, right? I mean, look at it. This is the domain of her bank account. The URL doesn't contain any malicious code, so it looks legit. And Java decides to click it, and let's see what happens now. So the request, at first, arrives at the caching mechanism. Now, the caching mechanism is not familiar with this file yet, so it asks the web server for it. Now, the web server receives this request with this non-existent triggering URL, and it returns a 200 OK response, meaning the URL stays the same with the content of Java's bank account, with their own private and sensitive content. So this is sent back to the caching mechanism. Now this caching mechanism receives this file and needs to decide whether to cache this file or not. So let's say that the configuration of this caching mechanism is to cache all static files, no matter what their caching headers are, because nothing sensitive can be included in static files, right? Like style sheets, usually JavaScript, images. So it caches all static files and disregards their caching headers. Okay, so in order to decide whether to cache this file or not, it takes a look, the caching mechanism takes a look at the end of the URL and sees that it has a CSS extension. So therefore, it decides to cache it, again, with Java's private and sensitive content of her bank account. This is now cached in the caching mechanism. In the next phase, this file is sent to the user's browser, but that's not interesting at all, because what's interesting now is that the evil twin can just take this URL and access it on their own without being authenticated to the application. Now the caching mechanism is familiar with this file, right? It just stored it. So it just sent it back, again, with the user's private and sensitive content back to the attacker's browser. We just exposed all of his private information. Very simple, pretty bad, and this is how web cache deception works. Now, this is bad, but it could get even worse than that. Let's say that the content of the HTML contains CSRF tokens. Okay, so now the attacker can use this CSRF token in order to attack the user with CSRF attacks. It could get even worse than that. In two web applications that I found to be vulnerable, the HTML contained the user session identifier. So now the attacker could take this session ID and use it to take complete control over the user's account. And that's really bad. Okay, so now we know how web cache deception works, and let's see a demo to better understand how we can identify whether our website is vulnerable or not. Okay, so here you can see our web application written in PHP. It's open on the left on Chrome browser and on the right on Firefox. We are now unauthenticated. there is a private page called private.php that you can only see while you're authenticated, and it presents for each user his own private content. Now, this web application is stored on an Apache server or an AWS, but it's also served by the Cloudflare CDN. So you can see that if we try to access the private page right now, we are redirected back to the login page, right? Because we are unauthenticated yet. If we try to take a triggering URL, we take the private.php page, add the name of a non-existent file afterwards with a static extension. We are redirected to the login page also, because there's no such page yet. OK, so let's log in using the admin account. OK, so now we are logged in. You can see that we are in our private PHP page. We can see our own private and sensitive content of the admin account. And now let's access the triggering URL. Let's add after private.php a trailing slash and logo.png. You can see that we receive a 200 OK response. The URL stays the same. And now the file is cached on Cloudflare servers. So we take this triggering URL and we put it on another browser while unauthenticated or on another device, and we get our content straight from Cloudflare. This is how web cache deception works, and in this case, this application is vulnerable to web cache deception. OK, so I found this vulnerability a few months ago in various websites, including PayPal, and let's see how it looked like when PayPal were vulnerable to web cache deception. So here you can see I'm logged in my homepage in PayPal. You can see some sensitive information here. It's canceled right now. We'll try to access a triggering URL. We're going to add after the homepage a name of a non-existent file with a static extension, and we receive a 200 OK response. The URL won't change, and in this case, the file is cached on Akamai in this case. Now we open incognito mode. We are unauthenticated. We access this triggering URL again. And look at it, we just get it straight away from the Akamai servers without being authenticated. We easily exposed the user's private content. OK, so what are the conditions for web cache deception to exist in a web application? Let's have a look. So the first one is that web cache functionality is set for the web application to cache static files based on their extensions, meaning according to the end of the URL. Okay? And disregarding or overriding any caching header. We need the web application, the caching mechanism to overwrite or disregard any caching header because, as I told you at the beginning of the talk, you know that the file for the triggering URL arrives from the web server with a no cache directive. And this is why we have the caching mechanism to cache all static files no matter what their caching headers are. Second condition is that when accessing a page like home.php, which is an actual page in the application, slash a name of a non-existent file, the web application will return the content of the actual page of home.php for that URL with a 200 OK response, so the URL stays the same. And one last condition is that the user has to be authenticated while accessing the triggering URL. OK, so after I posted about the web cache deception attack first a few months ago, some people asked me some why the hell questions. They didn't understand why the hell from the beginning some technologies that are involved in this attack, like caching mechanism and web frameworks, why will they meet these attack conditions from the beginning? So I picked up two of my favorite why the hell questions, and let's have a look at them. So the first one is why the hell would a web application react like this? Why will it return a 200 OK response for a non-existent URL with the content of the actual page? So let's see an example on a Django web application. So here you can see a Django web application. There's a page called inbox that returns the content that you can see right now on the screen. Now, some short background about how Django works. So when a request arrives at the Django web application, it goes through a dispatcher. And this dispatcher is configured in files called URLs. And in these files, the developers can use regular expressions in order to find a match. In order to find a match in the URI, and according to it, return the relevant content to the user. So this is an example of a standard regex that someone might use for his Django web application. It looks for inbox, then a trailing slash, and if it finds it, it returns the content of this page. So what happens if we have this configuration for the Django web application and we access this triggering URL, slash inbox, which is an actual page, slash a name of a non-existent file with a static extension. So in this case, we received a 200 OK response, the URL stays the same, and we receive the content of the inbox page. This is fantastic for us, right? Not very much for the developers, but it's fantastic for us, right? But why is that? Because look at the URI of the triggering URL. It starts with inbox, then it has a trailing slash. That's it, we have a match. Therefore, we receive the content of the inbox page with a 200 OK response. Now let's see another example of a poor configuration of this regular expression that works for a Django application, and it can assist attackers to create even less suspicious triggering URLs. So what happens if this is the regex that is used by the Django application? I just remove the trailing slash after the inbox. Okay, so in this case, if we try to access this triggering URL /inbox, and now we add .css, which doesn't mean anything, we still receive the content of the inbox page. This is awesome for us, right? Look at the URI. It starts with inbox. That's it. We have a match. Now, anything that comes afterwards, it just disregard by the Django application, and we receive the content of the inbox page. Okay, so if you want to solve this, if you want to prevent the Django application from returning the content of the inbox page for non-existent URLs, what can we do about it? So we just need to add one simple character, and that's the $sign and the end of the regex. So now, if we try to access this triggering URL again, we receive a 404 error. And now web cache deception can be exploited for this web application. And why is that? Because the triggering URI starts with inbox, then it has a trailing slash, but it doesn't end here. So we don't have a match, and we receive an error, and now this issue is fixed. No web cache deception for this application. Okay, and let's move on to the second why the hell questions. And this is, why the hell would a caching mechanism we act like this? Why the hell would a caching mechanism first identify the type of file that it just receives according to the end of the URL, and second, why will it override or disregard the caching headers that arise with the file from the web server? So let's have a look at two examples. So the first one is IIS ARR. ARR, for those of you who was not familiar with it, stands for Application Request Routing. That's a feature that makes IIS a load balancer. So in IIS ARR, you can set your own caching rules. It looks like this. And look at the bottom. It's marked in yellow. In order to identify the type of file that needed to be cached, it uses a wildcard and identify the type of file according to the end of the URL. And looks at the top. You can always apply this rule, meaning it just disregards the caching headers that arrive from the web server. So if we have this configuration for the IIS load balancer, IIS ARR, and we access this triggering URL, welcome.php page is an actual page in the application, and we add a name of a non-existent file afterwards, then if we have a look at the caching directory on IIS, we can see that there is a new directory just created named welcome.php. And inside it, there's a new file, a new cached file called test.css. But test.css doesn't really exist on the web application, right? But you already know what's inside it. And that's the content, the private content of the user welcome.php page. Let's see another example. Let's talk about a CDN. Cloudflare. Now, I must say a good word about both Cloudflare and Akamai. They both can meet the attack condition, and many websites on the web use their services. So after I posted my blog a few months ago, they posted their own blog explaining about web cache deception and how to prevent it, which I respect. Okay, so let's have a look at how Cloudflare server decides whether to cache a file that he gets or not. So in order for a file to be cached on a Cloudflare server, it needs to go through two phases. Now, the first phase is called the eligibility phase. And in this phase, the server takes a look at the URL and, according to the end of it, looks for one of the following static extensions. You can see here CSS, you can see here JavaScript, some images file, Microsoft Office files, torrent. So if the URL ends with one of the following extension, we just move on to step number 2. And you already know how you can make the web server send the content of a private file of a user with one of these extensions. Okay, so we move on to phase number 2. The last phase, by the way. So this phase is called the disqualification phase. And in this phase, the server takes a look at the caching headers of the file that it just receives from the web server. Now here we have a problem, because you already know that the file arrives from the web server with a no cache directive, meaning the file won't be cached. But exactly for that, we have Edge Cache Expire TTL to the rescue. Now there's a feature that you can set in your Cloudflare environment called Edge Cache Expire TTL. It was released by Cloudflare around 4 years ago, and it posted a blog to explain why you should use it. Let's read a part of it. So the title was Edge Cache Expire TTL, easiest way to override any existing headers. Sounds interesting, right? Let's read more. With Cache Everything, we respect all headers. If there is any header in place from the server or CMS solution like WordPress, we will respect it. However, we got many requests from customers who wanted an easy way to override any existing headers. Today, we are releasing a new feature that does just that. Fantastic, right? The customers of Cloudflare wanted an easy way to override any existing headers that arrive from their own web server. So they just need to set the Edge Cache Expire TTL setting in their Cloudflare environment, and that's it. Caching headers are overridden by Cloudflare. And this is why Cloudflare and Akamai works in a similar way. They both can meet this attack condition. Okay, so how this can be prevented? So there are a few ways to do so. You can only cache files if the HTTP caching headers allow. Now here, sometimes there are good reasons to disregard or to override the caching headers that arrive from your web server. Now, if you can avoid it, then you probably should. But if you need to override or to disregard these caching headers, there are other things that you can do in order to prevent your application from being vulnerable to web cache deception. Let's have a look at them. Another option is to store all static files in a designated directory and to only cache this directory. You can also cache files by their content type HTTP response header. Now here you depend on the technology of the caching mechanism that you are using. Some of them identify the type of file that they receive according to the end of the URL, according to its extension. Some of them do it according to the content type HTTP response header. Some of them let you choose, like Nginx. So if you can configure your caching mechanism to do it by the content type HTTP response header and not according to the end of the URL, then you should do it. And another option is to not accept these triggering URLs. Don't let your application to be so permissive. For URLs like home.php, which is an actual page, / nonexistent.css, don't return a true 100OK response, just return a 302 or a 404 error instead. So later on today, I'm going to release a white paper explaining all about web cache deception, and it includes some additional technologies that can meet the attack conditions, like Nginx, ASP.NET, and PHP, and everything you just seen in this talk. So thank you very much for being here today. I really appreciate it, and enjoy Vegas.